This video is about analyzing half-wave rectifiers. How do they work, and what is their output voltage? Here's a simple half-wave rectifier. It has one diode in series with the load. This one also has a step-down transformer to reduce its output voltage. The input is an AC voltage. If a transformer is used, the input voltage is applied across the primary winding. The output is a DC voltage because it does not reverse polarity. Unlike the output of a battery, however, this voltage doesn't have a steady level. This one has an AC voltage of 120 RMS volts with a frequency of 60 Hz. The step-down transformer has a turns ratio of 5:1, and the load has a resistance of 1 kiloohm. Let's calculate the peak value and the average value of the output voltage. First, we must convert the input RMS voltage to peak voltage. To convert RMS voltage to peak voltage, simply divide the RMS voltage by 0.707. The peak value of 120 volts RMS is 170 volts. Next, we must determine the peak voltage across the secondary winding of the transformer. Because the turns ratio of this transformer is 5:1, that means the output voltage will be 1/5 the input voltage. Dividing 170 peak volts by 5 gives us a secondary output voltage of 34 peak volts. Finally, we can now determine the peak voltage across the load. The voltage across the transformer's secondary winding begins rising toward 34 volts. If we use the constant voltage model for the diode, it starts conducting when the voltage reaches 0.7 volts, which allows current to flow and causes voltage to appear across the load. The maximum load voltage in this case is 34 volts across the secondary winding minus 0.7 volts across the diode, which is 33.3 volts. As the secondary voltage drops towards 0 volts, the load voltage decreases with it. Finally, the input voltage drops below 0.7 volts and the diode stops conducting. With no current flowing through the load, the voltage across it is 0 volts. The input voltage reverses polarity and begins dropping toward minus 34 volts. Because the diode is now reverse biased, no current flows through the load and the voltage across it remains 0. That means all of the applied voltage must drop across the diode. The maximum reverse voltage across the diode, called peak inverse voltage, or PIV, will be 34 volts. Finally, the secondary voltage will return to 0, and the load voltage remains 0 because no load current flows through this half of the cycle. Then the cycle repeats, producing a pulse DC voltage with a peak amplitude of 33.3 volts. But what is the average voltage? For a half-wave rectifier, the average voltage, also called the effective voltage, is 0.318 times its peak value. In this case, it is 10.6 volts and is the DC voltage. The red line shown here indicates the average voltage. The area of the curve above the red line during the first half of the cycle is equal to the area under the line during the second half of the cycle. They average out. Although the output does have an average value, it varies constantly and is almost always either higher or lower than that. We need to level it out. Putting a capacitor in parallel with the load helps to do this. Recall that a capacitor opposes the change in voltage. The resulting output is much smoother as shown here. The peak voltage is still 33.3 volts. But what is the new value of the average voltage? If you draw a line through the middle of the ripple voltage, you can see that the area of the curve above the line in the first half cycle is equal to the area below the line during the second half of the cycle. That means the average voltage is the peak voltage minus 1/2 of the ripple voltage. All that is left to find is the peak-to-peak ripple voltage. We can then plug it into the equation and find the average load voltage. Recall the equation for current in a capacitor. We can approximate it using algebra. In this approximation, delta V, the ripple voltage, is what we must find. Delta T is the period of the output voltage, which we already know. It's 16.7 milliseconds for 60 Hz in a half-wave rectifier. We also know the capacitance, 47 microfarads. Finally, we know the average load current that flows through the capacitor when it discharges. It is approximated by dividing the average voltage without a capacitor by the load resistance. We have 10.6 milliamps. Now, some of you may be uncomfortable with using an approximation for this calculation. You may be accustomed to using differential equations to obtain exact circuit values at any instant in time, and you believe that we should be doing that here. The reality is that circuits containing transformers, capacitors, and semiconductor diodes just aren't that precise to begin with. If you actually measured the output of a dozen so-called identical circuits, you would have a dozen different results. The capacitor alone usually has a tolerance of 20% or more. Plugging in the known values and rearranging to solve the ripple voltage gives us 3.77 peak-to-peak volts. That's delta V. Replacing delta V with 3.77 volts in the original equation for finding the average load voltage gives us 31.4 volts DC. Look how much smoother and higher the output voltage is just by putting a filter capacitor in parallel with the load.